OTDR, Optical Time Domain Reflectometer. The OTDR is an instrument to test the fiber length and determine if there are any broken fibers in the span. We will see more about OTDRs in this session. At the end of the session, you will be able to explain OTDR and its working. OTDRs launch short-duration light pulses into a fiber and as a function of time after the launch, then measures the optical signal returned to the instrument. OTDR injects light pulse and analyzes the backscatter and reflected signal. The received signal is plotted into a backscatter X by Y display in decibels versus distance. OTDR only needs to have access to one end of a fiber to make its measurements. An OTDR takes thousands of measurements along a fiber. An OTDR calculates the fiber distance by calculating the speed of light in vacuum and time divided by the index of refraction. Working of OTDR. OTDR uses the effects of Rayleigh scattering and Fresnel reflection to measure the characteristics of an optical fiber. By sending a pulse of light into a fiber and measuring the travel time and strength of its reflections from points inside the fiber, it produces a characteristic trace or profile of the length versus returned signal level on a display screen. Measurement with OTDR. Now, let's see how to measure with OTDR. First, switch on the OTDR. As you can see here, there are 4 keys as shown: the file key, the setup key, home key, and cancel key. First, press the setup key. Now from the options, select the acquisition mode. As you can see, there are 2 modes available: the auto mode and the manual mode. Auto mode. Auto mode is used in situations where the distance is unknown. The parameters like range, pulse width, resolution, time are automatically set in this mode. Manual mode. If the distance to be measured is known, we use the manual mode. In this mode, the parameters like range, pulse width, resolution, time need to be set. Connect the OTDR cable to the fiber distribution panel to which the fiber is terminated and then press the Start button. The OTDR displays the connection status. That is, whether the connection is good or bad. The red line shows acquisition in progress and the pulse width is sent for an average time of 20 seconds. As you can see here, if the fiber is cut, it can be detected as the trace goes down at that point. As you can see, the total distance shown is 9.907 kilometers, which is the total fiber length. The laser beam cannot travel further. In this example, there are 17 events shown. Each of these events are fiber loss points, loss due to connectors, splice points, etc. The total loss is 8.806 decibels. Observe that at point 1.602, there is a loss of 2.925 decibels. This loss is at the patching point where the fiber is connected to another fiber to terminate to a site. It is a high loss point. Point 4.957 is another patching point. The loss here is 0.243 decibels. However, here there is comparatively less loss. In this way, we can analyze each event in the cable network. Let's now see the factors that determine the signal variation in OTDR. Attenuation, also called fiber loss expressed in decibels or decibels per kilometer, represents the loss or rate of loss between 2 events along a fiber span. Event loss is difference in optical power level before and after an event expressed in decibels or dB. Reflectance is the ratio of reflected power to incident power of an event expressed as a negative decibel value. The higher the reflectance, the more light reflected back, the worse the connection. A minus 50 decibel reflectance is better than a minus 20 decibel value. Optical return loss, or ORL, is the amount of light reflected back from a feature. OTDR is able to measure not only the total ORL of the link, but also section ORL. How to interpret an OTDR trace? Front-end reflection is the connection between the OTDR and the patch cord or launch cable. It is located at the extreme left edge of the trace. Connector mechanically mates two fibers together and creates a reflective event. Fusion splices thermally fuses two fibers together using a splicing machine. Gainer is a splice gain that appears when two fibers of different backscatter coefficients are spliced together. Macro bending results from physical bending of the fiber. Bending losses are higher as wavelength increases. To distinguish a bend from a splice, two wavelengths are used, typically 1310 and 1550 nm. Mechanical splice mechanically aligns two fibers together using a self-contained assembly. Fiber end or break occurs when the fiber terminates. The end reflection depends on the fiber end cleavage and its environment. Ghost is an unexpected event resulting from a strong reflection causing echoes on the trace. When it appears, it often occurs after the fiber end. It is always an exact duplicate distance from the incident reflection. Bending. Large noticeable bends and microscopic irregularities can both attribute to loss in a fiber. Now let's see typical attenuation values in an OTDR. 0.2 decibel per kilometer for single mode fiber at 1490, 1550 and 1625 nm or nanometer. 0.35 decibel per kilometer for single mode fiber at 1310 nanometer or nm. 1 decibel per kilometer for multimode fiber at 1300 nanometer. 3 decibel per kilometer for multimode fiber at 850 nanometer. 0.05 decibel for fusion splice. 0.3 decibel for a mechanical splice. And connector pair loss is 0.5 decibel for a single mode connector pair and 0.75 decibel for a multimode connector pair. With that, we've come to the end of the session. In this session, we have learnt that the OTDR is an instrument to test the fiber length and determine if there are any broken fibers in the span. OTDR uses the effects of Rayleigh scattering and Fresnel reflection to measure the characteristics of an optical fiber. OTDR traces can be interpreted by front-end reflection, connector, fusion splices, gainer, macro bending, mechanical splice, fiber end of break, ghost, and bending.